Hello and welcome to the Unit 5 Forces and Newton's Law test review. So problem number 1. Dopey throws a diamond straight up with a velocity of 5 meters per second, then catches it. He noticed that it took half a second for the diamond to reach the top of the path. What was the diamond's maximum height? So there are two ways you can figure out which particular kinematic equation you need to solve this kind of problem. The first one is you can realize that I have a velocity of 5, so its initial velocity is 5 meters per second. The time is half a second, so time equals 1/2 a second. And if things are falling, you know the acceleration. The acceleration is gravity, which is negative 10. So you want to find delta x, so you want to use the kinematic equation that has vi, t, a, and delta x in it. Another way you could do it is you could just remember from the previous unit about projectile motion that whenever we have objects falling through the air, we want to use this kinematic equation. This is the most versatile kinematic equation, and we pretty much use it whenever things are falling. So now all we have to do is plug in the numbers. It gives us an initial velocity, a time, and the acceleration we know is negative 10 because it's gravity. So when you plug the numbers in, what you get is, alright, the delta x equals VIT, so that's 5 times a half, plus 1/2 times a times t squared, which is 1/2 times negative 10 times 0.5 squared. So you plug in all those numbers, and then what comes out of the calculator is so you get that delta x, or the displacement, is 1.25 meters. Number 2, Sneezy was walking at 1.2 meters per second, then he needed to run to get a tissue. He accelerated for 6 seconds, reaching a final speed of 3 meters per second at the tissue box. What was his acceleration? So this question relies on the definition of acceleration, which is the change in velocity over time. And in order to figure out the change in velocity, we need to know the difference between the final velocity, which is right here, 3, and the initial velocity, which is 1.2. So we take the difference in that over the time, which is 6 seconds. So what that gives us is the final velocity, 3, minus the initial velocity, which is 1.2, over the time, which was 6 seconds. So you do 3 minus 1.2 over 6, and what that gives you is a final acceleration of 0.3 meters per second squared. The last one you need to calculate here, number 3, Grumpy doesn't rush anywhere. Every day he walks at a steady, straight line to work, which is 140 meters away from his house. His walk always takes him 90 seconds. So what is Grumpy's velocity? This relies on you knowing what the definition of velocity is. It's really similar to the acceleration definition. Velocity is the change in position over time. And in this particular case, you don't even need to subtract anything because it tells you how far he goes. He goes 140 meters, so this is his change in position, and the time is going to be 90 seconds. So to get the velocity, you simply plug in the numbers, and you get that it is 140 over 90. So 140 over 90 gives you 1.56 meters per second. So number 4, 5, and 6 are only useful for answering number 7, so let's jump down there. Which of these particular things had an unbalanced net force acting on them? So you need to know what an unbalanced net force is. It happens when the forces do not entirely cancel. So that means that you have forces like maybe one up, one down, one left, and one right. Oh, I messed it up. Right and left, whatever. The up and down forces will be the same. Now, the left and right forces, well, the left one cancels out some of the right one, so you get something like this with a little bit smaller force. I keep getting this mixed up. The right one cancels a little bit of the left one, so you get a force like this. And this is an unbalanced net force, because after you canceled out all the forces that you could, you still have some sort of force arrow. Now, whenever you have an unbalanced net force, you have an acceleration. So basically, what you see is if the acceleration equals 0, then there is no unbalanced force. But if the acceleration is not 0, then there is an unbalanced force. So all you look for is an acceleration. If there is an acceleration, then there is an unbalanced force. And if there is no acceleration, then there's not. So I'll do something different. I'll just give you all the answers and then explain it in a second. Okay, so Dopey's diamond from the first problem is being affected by an unbalanced force because gravity is accelerating it downwards at negative 10 meters per second squared. So because there is an acceleration, there's an unbalanced force. Similarly with Sneezy, we calculated the acceleration, so there is an unbalanced force. Now Grumpy goes in a straight line. It takes him the same amount of distance and the same amount of time every day. You could say he accelerates when he starts, like as soon as he goes from stopping to starting his walk, but during the walk he has no acceleration because he's moving at a constant velocity. Doc is accelerating because he starts moving. He stands still for a few minutes, right? Stands still, and then started moving. So the VI is 0, and the VF is not 0. It's something else. So he changes his velocity, which means that he accelerates. With Bashful, you might not think he accelerates because you have 2 meters per second and 2 meters per second, but he's starting off going north, and then he ends up going east, like this. So east. And if the arrow changes at all, if it changes the direction or the magnitude, then it is accelerating. And if it is accelerating, then it's being affected by a net force. So Bashful is also being affected by a net force, and then Happy, right? He slides down, and then he stops. Right here at the point where he stops, he's being affected by the force from the ground. So he is being affected by an unbalanced net force. Now, what is the name for an object's tendency to resist changes in its motion? This is a vocab word that's good to know. The definition of this tendency is inertia. Next, we have vector qualities. Now, a vector has both a magnitude and a direction. Anything that I have ever represented by an arrow in this class is a vector. Anything that I haven't isn't. So speed is not. You just read it off of your speed dial speedometer. No arrow. Velocity is, though. Distance is not. It's just like it's 3 miles away. You don't need to give me a direction. Time is not. Displacement is, because you say that it's 3 meters east, maybe. Displacement is the vector version of distance. Direction is not, because you need direction and magnitude to be a vector. Force is, we draw arrows for force. Inertia is not. Acceleration is, because gravity accelerates you downwards, right? So it has directions. Volume is not. You're not 3 liters east. You're just 3 liters big. Magnitude, well, you need a magnitude and a direction. And then mass is not. Sorry. Mass is not a vector because mass doesn't have any direction. You're not 6 pounds up. You're just 6 pounds. Mass isn't even pounds. That's a force. You're not 6 kilograms up. You're just 6 kilograms. Mass is not the same thing as weight. I shouldn't have done that. Sorry. So now we got an actor standing on a stage. The normal force on the stage, the normal force of the stage on the actor is 700 newtons. So you got a free body diagram, which is all the forces represented as arrows. You got the actor and the normal force, which is 700 newtons. Now, in order to have a normal force, you need to have some sort of force pushing you towards an object. Normal force is what happens when an object resists a solid falling through it. So specifically in this class, normal force is normally going to be the result of gravity. So you also have a gravitational force pushing down. You know that because when an actor is standing on a stage, he's not falling up, he's not going into the air, and he's not falling down into the earth. He's not moving at all. So the forces that are on him cancel. So the upwards normal force gets canceled by the downwards gravitational force. So this is the normal force, and this is the force of gravity. Now the actor's weight. Well, the definition of weight is the force of gravity acting on an object. So we know the force of gravity, it's 700 newtons. So 700 newtons is the actor's weight, and it should be capital. So now, what is the actor's mass? This is kind of annoying, but you know that F equals ma. That's Newton's second law. And you know that weight is the force of gravity. So this is a weight, and you know that gravity accelerates things downward at 10 meters per second squared. So F equals ma, written more specifically for weight and mass, looks like this. Get the force of gravity, which is weight, equals m times the acceleration of gravity, which is negative 10 meters per second squared. So what you do is the weight divided by 10 is going to give you the mass. So the weight over 10 equals the mass. And you might say, wait a minute, there's a negative here. Where did the negative go? Well, basically, you can't have a negative mass. If you want to be really technical, weight is just the magnitude of the force of gravity. It's really directed downwards. So you'd put a negative to tell you that it's directed downwards, and the negative on the weight and the negative on the 10 are going to cancel. But don't worry about it. If you just get a negative mass, remember that you can't have a negative mass, so make it positive. So the weight is 700. 700 divided by 10 is 70. So this actor weighs 70 kilograms. Not weighs, it's the mass. Sorry. The mass of the actor is 70 kilograms. So if you have a 76 kilogram actress on the stage, who has more inertia? Well, inertia is directly proportional to mass. The more mass you have, the more inertia you have. It's harder to move you if you're heavier or more massive. So the actress is going to have more inertia because she has more mass. More mass. Great. So two differences between weight and mass. Well, one we talked about just before. Weight is a force, but mass is not. It's just a quality of an object. So that's one difference. And as a result of that difference, they are also measured in different units. Weight is measured in newtons, and mass is measured in kilograms. So next we got the word equilibrium. Something is in equilibrium if there is no net force acting on it. Alternatively, which is the same thing, you could say that equilibrium is when an object is not accelerating. So no net force or not accelerating. So now we get into SI units. These are the things that let you know what the number in that problem is supposed to be telling you. Is it telling you a mass or a time or a distance? You don't know unless you look at the units. They tell you. So the unit for mass is going to be kilograms. You often see it as grams, but kilograms is the official SI unit. Displacement is measured in meters. and then time is measured in seconds. These are some fundamental units, and most of the other quantities we have are built out of these. So that's a S, not a G. S for seconds. Velocity is going to be how far you go per unit of time, so it's in meters per second. Acceleration is how much your velocity changes per second, so it's meters per second, which we often write as meters per second squared. Weight is a force, so it's going to be measured in newtons. All the other forces are also measured in newtons, so force is in newtons, friction is a force, which resists motion, then tension is the force in a rope. And finally, we have inertia. So some people will tell you that inertia does not have mass, and some people will tell you that the units of inertia are kilograms. So I'll put kilograms in blue to let you know it's kilograms-ish. It depends on who you ask. Inertia basically is the same thing as mass, though. So list two field forces. The only two you have to care about in this class are going to be gravity and electromagnetism. The other field forces generally act inside the nucleus of atoms and are not things you deal with in the everyday world. Three contact forces. Well, friction is a big one. Friction. Air resistance is another one. It might not seem like it because a contact force and a field force are different because a field force acts at a distance, like without actually physically touching the object, but a contact force has to touch something. And you might say, well, when you feel air resistance, it doesn't seem like you're touching anything. There's no obvious brick hitting your face. But what's happening is little air particles are bouncing against you. The air particles like this have to physically hit you to bounce off. And then when they bounce off, that's what you feel as air friction or air resistance. So, contact forces, you got friction, you have air resistance, and then you have, let's say, tension. Tension is the force in a rope, right? So if somebody's pulling you, they're applying a tension force to a rope on you. Then I actually just added normal force. Normal force is the force of a solid that is not allowing you to move through it. So like a table is solid because it applies a normal force to your hand when you try to move through it.